New Year's waiting. There is still somebody waiting for me. That's nice.
You should give him a bonus or something.
Yeah, definitely. Whoever is there, I need to give some extra
Maybe
thing.
it's me
Yeah,
because
it's
you're
you.
bartending.
Yeah, probably you.
So I can get the bonus.
Yeah. Okay, so it's gonna be this one, and I will put it active. So how is it? Is it okay already, or can I just go now? I will put this in at this present.
It's 5
No.
seconds delay and everything.
Yeah, it looks very good. Yep. But I'm here. How is it? How is it?
It's fine, but there's a problem here. This
Yeah, this is not okay. I need to change that. Okay, maybe I instead of sharing. Display. So it's a display capture. That's what I would like to use, not this one, but display capture. Okay, so it's active and on. Good, but not displayed well to online participants. Okay, so looks good. Looks good to me. Yeah, looks good to me. All right, so what's going to happen today? So we're going to spend this 45 minutes to try to close the case about model reduction. And if, how is my voice, by the way? Is the voice on?
uh for yeah, it's like 5 seconds of delay and
5 seconds of delay, and this is not displaying well, so I need to show
so
this HDMI one.
when do you think that it's going to be finished?
We're going to close at 2, 2 o'clock.
Two, okay.
What about this guy? Why this is not willing to work now? So what should I do here? This is it. This is this P. What? Duplicate. Okay, now it's finally good to go.
Cool. And what about this side? Is it okay?
Yeah, it looks good to me.
Okay, cool.
Yeah, it looks okay to me.
That's
So it's
that's
not the
good.
perfect green screen, but it will do the job because we cannot do the more no more tuning here, so it's okay. So maybe if you can, so let me see where should I stand? Here.
Do you want me to?
Oh, it's okay. You can leave it there. I'm just checking where that I need to stand. No, it's here.
No, no. I have to bring it back. Like,
Okay, if you don't see me, you lose nothing.
no, it's okay.
Now it's okay. All right, very good. Like I say, so I need to put the sign to myself. So this is respect. The sign that I can cut the all this mess and all the tunings away. So that's for me. All right. So what I would like to do in these 45 minutes, 50 minutes perhaps, is that I would like to try to close the case of model reduction. There is a mix of different topics that I would like to discuss, and then we're going to move with these different topics. And one of the new topics that I would like to introduce you is a contact modeling. This is something that is taking us very close to the game technology. And I tried to explain to you what is it, how is it they do the contact descriptions in games and how they do that in multi-body system dynamics. Basically, This is something that if you have heard about the no smooth and non-smooth dynamics, is related to how you describe the contacts. Non-smooth is based on inequalities, something that you can say that, okay, the bodies that they can do whatever they want, but they cannot penetrate. And then the smooth dynamic is something that bodies can do whatever they want, including penetrate. They can get graphics to be penetrated, but based on how much they're penetrating, there is an extra magic force that will push them aside, push them away from each other. That's going to give you smooth dynamics. There's a role for smooth dynamics, but it's limited. How it is limited and how that is different than non-smooth dynamics, probably it's going to be next week that I'm able to explain that to you. But prior to that, we need to close the case about eigenvalue analysis and model reduction technique. We're very close to do so. There's a few more things that I would like you to be aware of. And that's it. That's it. Okay. This is a very lengthy summary of what we discussed. And I'm going to be very brief here. So it's all about that we get started from a full finite element model. And then what we wanted to do with the full finite element model is that we wanted to run the eigenvalue analysis. And based on the eigenvalue analysis, we can get the eigenvalues and corresponding eigenvectors. In theory, if you have a model with 100,000 degrees of freedom, you can get the 100,000 eigenvalues. These are these natural frequencies and 100,000 corresponding eigenvectors. 100,000 ways that the body can deform, and it's pretty clear that not all these 100,000 is significant. Some of them are more significant than others. And what happens if we're going to ignore the insignificant ones? Then we can reduce the size of the problem. And that's exactly what we do here in a model reduction technique. So we conduct the eigenvalue analysis. We get something that is an eigenvector, which is a way the structure can deform. How much this particular way will contribute will be unknown. That's going to be something that is called model coordinate. In our case here, the model coordinate is the one that is denoted as a P here. Okay, the pen is not willing to work. No, all right, never mind. You see the P here, so that's what it is. Now, if you do this conversion from nodal degrees of freedom to modal degrees of freedom, you can reduce the size of the problem. And the one beautiful middle or like the side effect will take place, and that's the fact that the new mass matrix and new stiffness matrix will be orthogonal, meaning that they will be a diagonal representation, making or simplifying the computation very significantly. So that's what the method is about. And we learned about how you do this thing. So in the eigenvalue analysis, very, very important to understand that there's nothing to do with the actual absolute responses, because when we're computing the eigenvalue, we're setting the force to be equal to 0. All right? And when we do that, then we can get these eigenvalues and eigenvectors. An example we looked was this beam structure, spring structure, and we were able to extract a total of 4 different eigenvalues and corresponding eigenvectors. So that's what we did a little while ago. Big question is this. Now, what we did in this case of spring structure was that we set no boundary condition. The boundary condition in finite element method means the way you construct your model to ground, the fixed coordinate system. That's what typically that means. Now, the boundary condition we used in the example that I just briefly browsed over was no boundary condition. All right? But in the real life, what would be the right way to set the boundary condition? And now the figure of the real problem you can see in a daily life is a crankshaft mechanism. In the crankshaft mechanism, I'm looking at this connection rod. Connection rod is something that is connected by a revolute joint, one end, another end is a revolute joint. Okay, what is the right way that we can define this boundary condition? Now, here's very important. The boundary condition that you set in your finite element software will be later in multi-body system dynamics, it will be called as a reference condition. Why? Because remember what we do, what's the big picture here? The big picture is something that we're describing the deformation with respect to reference coordinate system. What's the reference coordinate system? That is the one that is rotating and translating with the body. That's kind of the same thing that you have a global coordinate system in your finite element model. It has a lot of similarities, and it's okay to call this global coordinate system you have in a finite element model as a reference coordinate system in a multi-body system dynamics. Because what we do then is that we take the multi-body system dynamics and we're taking the large translation and rotations into account, and that with help of the reference coordinate system. But back to my question. Now, if you have this connection rod, how is that you can describe this boundary condition, reference condition, if you may? Should you just leave it floating in a space, which is this option A, or should you introduce a simply supported boundary condition such that there is a kind of like a revolute in the both end, or should that be a fixed coordinate system? So that's something that you need to solve when you do the practical modeling task. But what do you guys think? What would be the right way to do this? What do you guys think? What is the right way to do this? Now this is not so serious. We can just communicate it, but I still would like you to use a Socrative, because I said that it's easygoing and it's not serious, but it is, because I'm grading your performance based on this. So what I'm saying and what I'm doing is not the same thing. Okay, so what would be the right way to set the boundary condition, reference condition? And the options are method A, where there is a no boundary condition whatsoever. Then there is a method B, where there is a simply supported boundary condition used. Or method C, oh, is a Socrative is not on. Okay, hold on, just a second. Here, so let me take myself to Socrative. But Ezra, you did not fight back to me when I said that I will get started at 1 o'clock. You were, okay, yeah, it seems to be 1 o'clock. You knew that I'm wrong. You did not fight it back. They say, take your ass right, the lecture room right now, right here. Because, oh yeah, you have a good case because you have a time difference in your place. Yeah. Okay, so teacher, Pat. All right. How to set the boundary condition? Now it's on. And yeah, it seems to be. Let me take myself back to this slide where things are explained. All right, here it is. These are the options: A, B, C, and D. Team Malaysia, how is you casting your vote? How is you entering your answer? What is that? From A, B, C, and D. B, you both are agreeing with that? B? All right, then let's take a look what the others are saying. And one more thing that I need to find out from my backpack is this one here. Okay, my pen. Yep, I can write because I need to do some writing momentarily. Okay, are we okay? So can I close the in-class quiz? So we have 4 students only. I guess that's it today. All right. Everything is correct. You can do it any ways you want. Okay, but the answer for this question is you can do it however you want. This is very, very confusing. Like what? Because you know that boundary condition, how you set this to reference coordinate system will affect to the natural frequency, right? What is the lowest natural frequency will be different in this case, comparing this case, comparing this case. Come on, what is this? So how come you can get the same response? Now, here comes something that is extremely important to understand. What we do in multi-body system dynamics is that we are traveling to final location, which is a position of a particle. And if I try to highlight this situation using this drawing here, so let's say that we have let's say a cantilever beam like this, and a cantilever beam on the form configuration will be like this, and it is loaded by force in a free end. So what will happen is that it's going to experience the deformations roughly like this. Sorry that my writing is not very clear, but that's what's going to happen. Now, what we are interested in is that we would like to know where the end, actually all the particles, are located with respect to global coordinate system, which is this coordinate system here. All right, so let's see how we can do this situation. If we can use a boundary condition, reference condition A here, what will happen in this case is that the reference coordinate system is no longer attached to material point, none of the material point, but it is floating with the body. And when the deformation is this banana shape like this, the coordinate system will be somewhere here. All right? So you're going to move from global coordinate system to your reference coordinate system with the vector r. Then you're going to take orientation of reference coordinate system into account. And then with help of vector u bar, you're going to go here. Okay, what about second choice? Second choice, this becomes to be a little bit unclear, but let me try to change the color to make this more clear writing. So now, if I'm going to put like my reference coordinate system like this is corresponding to case B here. Again, I'm traveling first here, and then I'm traveling here. My final destination is same, so it's no different. And again, when I'm using this fixed boundary condition, this cantilever beam, again, I'm going to go here. My orientation will be different, but my final destination is all the time here. So what matters end of the day is the shape, not how it is associated with the reference coordinate system. I mean, the reference coordinate system is, of course, very important, but the most important is the shape. And if you compare these shapes, they are roughly the same. When you look at them, this shape, which is a banana shape, is roughly the same than this one, which is roughly the same than this one. And that's why in each of these cases, you can get roughly the same final solution. Now, this method we're learning here is called the floating frame reference formulation. The floating frame reference formulation. This means that the reference coordinate system is floating with the body. That's what it means. And this situation is exactly the one you can see here. You know, this, if I put this banana shape and I put my reference coordinate system here, you see that the reference coordinate system is de-attached to material point. It will be same that the material point if there is no deformation whatsoever. But as soon as there's a deformation, the reference coordinate system is floating with the body. So that's where the name is coming from. This is where the name floating frame reference formulation is coming from. So it's not rigidly attached, but it can be floating with the body. So it can be traveling, it still can describe the last reference translation and rotation, but it's not attached to material point. That's something that is pretty amazing. It will be attached to material point if there's no deformation, but as soon as there is a deformation, it will be detached from it. Okay, so what do you say? Any comments? Makes sense? Again, floating frame reference formulation, reference coordinate system is floating with the body. No comments. No arguments against. All right? So if not, then we're going to move on. Now there is a paper written by, no, not this. There is a paper written by Ahmed Shabana that this example is used, this cantilever, this crankshaft mechanism is used as an example. And he demonstrated numerically that you can use each of these three different reference coordinate system, and regardless what is your choice, you can get roughly the same response. It's quite surprising, quite surprising. But again, keep in mind that what we are focusing on is a final destination, where a particle is located. How you're traveling this location doesn't really matter. Doesn't really matter. Yes, this one. Okay. Right, like I explained, this was one of the paper written by Ahmed Sabana a long time ago, and he demonstrated that you can do it this any way you want. All right, but then comes to be difficult, really. Like practical cases, it may not be this simple. So maybe there is a more complicated connections, and it's not as straightforward than the connection rod. Connection rod is somewhat easy to understand, but in a real life, there may be more harder combinations, so it's going to be something that you need to work harder with. And that's something that we need to take a look at. We need to actually develop the method that is more general, because this is now based on how well you can set these boundary conditions. Sometimes you can do it correctly, sometimes you may not be able to do it correctly. So we need to find something that is more general than that. Okay, so this page was made to this here that I can explain this floating frame reference formulation. By the way, a funny thing about this coordinate system, if you think about this coordinate system, and let's put it this as a cantilever beam, and I'm pressing this upwards to make this shape to be more visible. So if I use this deformation shape here, this is where the point is located. And now the reference coordinate system will be here. You see the reference coordinate system is translating and rotating because of the deformation. So it's not just describing the large translation and rotation, but partly the deformation too. And because of this motion here, it is possible that this setup here will introduce a little bit of movement in an axial direction too, even though that we still have this assumption of linear strain displacement relationship. Remember what this whole idea about the linear displacement strain relation was a foundation of modal reduction technique. But still, when we use this assumption, you can get the certain amount of nonlinear deformation simply because of the floating feature of the reference coordinate system. Okay, makes sense. Kind of makes sense. All right, what the floating means in the floating frame reference formulation. It means that the formulation is still under development, so it's floating towards its final form. It means that the body inertia can fluctuate. It means that the strain within the flexible body can be defined easily. It means that the body reference coordinate system can move from a material point of the body. What do you guys say? Okay, let me take myself back. Discord. Okay, so there's more answers, but this time, oh, we got nine students still. How come? Okay, you don't see this, so let me put this visible to you. Duplicate. All right. It's different question. Oh, here it is. This is the right one. What the floating means in the floating frame reference formulation. This Craig pumped was, yeah, my mistake. It seems that I'm doing an awful lot of mistakes today. You agree? You should agree. You should agree with me. You should. Definitely, you should. Yep. Very good. Okay, so I got 4 answers so far. So there was a 9 answers last time. So we'll see then. Body inertia can fluctuate. It's like body mass can. It would be easier to say body mass can change. Okay, so we got the 5 views, 4 views at the moment, and you guys. Okay, Team Malaysia, what is your vote? How is your vote? Not easy. Your vote goes to what? Are you gonna pass this? You cannot. So what do you think? Oh, can you see this clearly? Okay. And your final vote is what? Okay, so where I got the 8 answers, and the last time it was 9. So I think the only one we're missing here is a Team Malaysia. So what the Team Malaysia is saying? D. All right. So the D is about the Team Malaysia is saying, and the D is correct. Ah, very nice. So we got very nice solution. We got close to 100%. So I think out of these 9 answers, the one only was incorrect. So most of was it you that voted incorrectly? Or you're not part of the competition? Maybe. No, we don't do that. We don't do that kind of thing. Okay, right. So the final story that I would like to tell, this guy. Final story that I would like to tell today is, like I said, in general case, it becomes to be difficult to set this boundary condition. It's not easy. It's okay and it's doable in a simple cases like connection rod, but in a general cases it becomes to be complicated. So that's why many commercial software they're using something that is called Craig Pumpton. You saw already that one of my in-class quiz was related to Craig Pumpton. But what is the deal with this Craig Pumpton mode? Is this, by the way, something you have heard about it earlier? Because I think that Jussi Sopanen is explaining about this. No, he's not explaining about the Craig Pumpton modes. Okay, this is a one way that we can get this deformation mode. And this is so much popular because this is offering something that is so much general. You don't need to have that deep knowledge about the finite element modeling to be able to use a Craig Pumpton modes. How it works is fairly straightforward. You take your finite element model and then you're selecting the points of interest, something that you feel that are important for you. And something that is important for you maybe because of there is a joint connection from that particular location to neighboring bodies, or there may be a joint, excuse me, no, force imposed to this particular position. And the force could be maybe due to the hydraulics, or there's a point force that you know that for sure will be appointed to this particular location of the structure. All right, now I have here an example structure, which is a plate structure. And I'm saying that, okay, the point of interest, it have to be, or need to be in this case, this corner, this corner, no, okay, not willing to do the drawings if I use this kind of presentation mode, but you see that there's in left side of the plate, there are 2 corners, each side of the plate, they are selected as a point of interest. Now the point of interest need to be named better. And the way we're gonna name this is like boundary degrees of freedom, because they are where the structure is connected to its neighboring boundaries, forces or joints. All right. So 2 nodal locations are selected as a boundary degrees of freedom. Now all these nodes and corresponding degrees of freedom will be selected as a one category of degrees of freedom. Rest, which will be much more than the boundary degrees of freedom, will be selected as an interior degrees of freedom. So it's going to be a lot of them. So if you think about this structure, there's a majority of degrees of freedom are internal degrees of freedom. 6, because this is a plate element. The plate element usually have a 6 degrees of freedom burden, not a location. 6 plus 6 is considered to be boundary degrees of freedom, a total of 12. Rest, 100 or something will be considered as an internal degrees of freedom. And now what we're going to do then is that we're going to make a revisit to our equation of motion. This equation of motion we're using in a finite element modeling to describe how is the performance of this plate structure. And this equation of motion consists of mass multiplied by acceleration, nodal acceleration this time, stiffness multiplied by displacement, and external applied forces. Now we're going to do the reorganization. So we're reorganizing rows and columns of these two matrices such that this boundary degrees of freedom will be pointed as a upper left corner of the mass and stiffness matrices. This is what you can do. So you can just keep on track what you do, but you can reorganize degrees of freedom as you want. So it's allowed to do that. All right, now this is how we organize things. And then we're going to do the computing. So the way we're going to do the computing is that we're going to take first a close look about interior degrees of freedom, meaning that just this lower left part of the mass matrix, lower left part of the stiffness matrix, which is in a size-wise is a big size, we're going to use them to compute eigenvalue analysis. And then we're going to compute something that is called static correction modes, and that will be based on these boundary degrees of freedom. Okay, so first step, we're going to take this interior degrees of freedom. You see that the lower left part of the stiffness and mass are used, nothing else, absolutely nothing else, no forces, nothing. And then we're going to compute eigenvalues and corresponding eigenvectors. All right? Then the next step is that we're going to forget about the inertia. We're going to forget about the inertia term as completely we can, and we can only look at the statics, which is a stiffness matrix multiplied by displacement, and that's equal to external applied forces. And that equation we used to solve interior degrees of freedom. Oh, let me try to do this. So we're computing this guy. All right. And when we're going to solve this guy from this upper equation, it's going to be like this. So it's going to be part of the stiffness that is related to interior degrees of freedom, and then some cross terms as well. You can get another set of modes. What these modes physically standing for? Well, let me give you an example. So if you have a beam structure like this, so this beam structure consists of this many nodes. And I'm going to select this one and this one to be my point of interest. This is where I know that it's going to be connected to neighboring bodies, or there is going to be a lot of force in both of these locations. So what happened then is that I'm going to first compute this set of modes, which is physically same than attaching these degrees of freedom to ground like this. You conducting the eigenvalue analysis for rest of the degrees of freedom, meaning that the lowest mode you can get will be something like this, or maybe this will be pointing upwards, something like that, and then the higher and higher frequencies. That's going to be the first set of modes associated to this computing. Second set of modes will be something that you introducing unit displacements to each of these boundary degrees of freedom, meaning that if now I need to take this drawing away a little bit. So if this was my structure, and that was selected, my boundary degrees of freedom mass was this one. So what you're going to do then is that you can attach each of these nodes to ground one at a time, and then you can introduce a unit displacement. This is one unit displacement, and you're going to see how is the rest of the degrees of freedom following that displacement. That's going to be associated to this set of modes. Okay? And then what you're going to do is that you're combining these modes. Something that is, well, this is a good picture. This is where this is a beam structure where this node in the left side, node in the middle, and node in the right-hand side are considered to be point of interest, boundary degrees of freedom. And we're going to, as you see, we're going to first conduct the eigenvalue analysis, and then we're going to introduce the static displacement. So they're going to be equal number of static displacement than boundary degrees of freedom. Now you can get two different set of modes, which are combined using this matrix definition here. And this is where we could end. We could end here, but there is a minor, I would say not even significant, but sometimes people are bothered with this problem we have here. And the problem is that, the static correction modes, because they are based on the one unit displacement, they are not mathematically orthogonal. Meaning that if I take myself back to the very first slide here, no, second slide. Remember what we did here? We started here. We used the eigenvalue analysis. We got this eigenvector or matrix of eigenvectors because this guy was orthogonal, meaning that each of the deformation modes were not related to each other. They were all independent. You were able to get this stiffness and inertia that were diagonal representation. Now we cannot get this same solution because these modes we're going to get from this Craig-Pompton are not orthogonal because of the static correction mode. Static correction mode is not independent, but it's a combination of previously known modes. So it's not able to give you this diagonal representation. I feel not the major problem, but some people say, okay, this is such a big problem, we need to fix it. And you can fix it if you want. And the way you can fix it is called, it's a very, very complicated name. It's called orthonormalization. How it goes is this. All right, so this is what you're going to get. So this is my set of modes, which is not orthogonal, simply because this guy is based on the unit displacement and they are not vibration mode. And if it is not vibration mode, it's not orthogonal. So you're going to get this set of modes. And what you're going to do then is that once you compute your stiffness and mass based on this set of modes, they are not orthogonal. This will be including terms that are non-diagonal. Off-diagonal terms will be non-zero. And you can get rid of that by simply taking this new stiffness and mass and introducing another set of eigenvalue analysis, which is called orthonormalization. You put them in one same package. You're forcing things to be orthogonal. And when you do that, you will get the new set of modes. And based on this new set of modes, you will get absolutely diagonal stiffness and absolutely diagonal mass. What is going to happen in this phase when you're introducing eigenvalue analysis again is that you can lose a physical interpretation of the modes. You can get something that is roughly, approximately free modes and something that is approximately local deformation due to the forces. Roughly free modes is this. Boundary modes where there's a heavy local deformation will be the ones that are very good to capture the force deformation or the deformation due to the forces in the beginning. Those will be this another set of modes. And that's how it works. So that's a Craig-Pompton method. How you guys like about the Craig-Pompton method? How you can then, in real life, how you can select these modes? Well, the most strongest tool selecting the modes is your engineering brains, sometimes called as an engineering sense. It's not the same as the common sense. Common sense and engineering sense are related. They're cousins, but they're not the same thing. Engineering sense is more powerful than the common sense, because I don't know why, but it seems to be like that. Because engineers are well educated. That's common sense is a common people. Engineers is better than a common people, right? No comments. Okay, all right. Engineering sense is important because the way the structure deforms, you can already make a good decision whether or not this makes sense. Because if you see that, okay, let me give you an example. Okay, I'm not very good to draw a picture, but this is beam structure that is a three-dimensional representation like this. If your loading will be in this one axis, like up and down, the most probably the modes that are off plate are not significant to you because you have no loading in that particular direction. So you can easily ignore modes that are not in a line, and not in the same direction than the fours are. So that's what I mean about the common sense. And then of course you can select them automatically. And how it goes automatically is something that I need to explain a little bit. This is a little bit complicated things to explain, but strain energy, what I think I can call that U is a strain energy that which is like this. Okay, this is a strain. This is a matrix of elastic coefficient. This is a strain again. All right, so this is how you can compute the strain energy. You see that each of the modes can be extracted from the strain, because you know that strain and displacement are related, and also you know that displacement and modal coordinates are related. For modal coordinates, you can get the nodal degrees of freedom, and nodal degrees of freedom, you can get the strains. All right. The P is for each of the modes, so you can compute how much is a contribution of one single mode. But what you can do before that is that you can give the full set, meaning the high number of modes, as high as possible, higher the better, I would say, and you can compute how much is the total strain energy. You could get the numerical value, which is, let's say, 100. Let's put it 100 because it's easy to think about it. And then you're going to start looking where this 100 is coming from, because the 100 is obviously coming from the number of modal coordinates and corresponding modes. How much P1 is corresponding to this 100? How much P2 is corresponding to the 100? When you're adding them all together, you're going to get the number 100. You're going to be surprised to see it, that the contribution is not equally distributed, but it's going to be only, well, typically in the practical cases, it's going to be something like this. So if this is going to be this 100, and then this is just the ID of P. So the first one is probably contributing as much as, well, let's say the one of the lowest ones is contributing as much as 90%. So if I put here number, this is 100, this is 90, so it's 90%. Then there's going to be one more that is contributing 5%, and there's going to be an awful lot of very small deformation that is contributing a lot less, meaning that their contribution can be below the threshold value. And the user can define the threshold value, saying that, okay, if your contribution is less than, let's say, 0.1%, I'm going to kick you out from the community. So if you're a very productive member of the community, they will keep you in a play. But if you're contributing less than 0. something percentage, they will kick you out from the village. So that's what's going to happen. And now that's the selection. Now this is this automatic selection that is introduced in most of the commercial software. So first, you compute like how is the commonwealth of the entire village, and then you're checking how much each of the individuals are contributing to commonwealth. That if your contribution is less than preset value, you will be out. Okay, we get out from these less productive members. How much we can lose? Not much, because remember their contribution is less than 0.1%, and then everything out of that is kicked out. So how much you can lose the accuracy will be insignificant. Very rough world. You know that you may think that okay, the nature and the wildness is rough. It's not. You know, more wilder and more harder life is multi-body system dynamics, because we kick off those members that are contributing very less, and we don't care. Now it seems that you don't care actually is my stories today, because but anyways, that's how it is. This is this automatic selection process. I guess there is no point to ask like if there's any comments, any questions. Makes sense. Is it making sense? Yes, sir.
So that doesn't take any action about, or isn't dependent on the force factor.
Yes, that's the big problem in this automatic selection process. It is based on this scenario you're running the entire strain in it. Now, if you're running the strain energy by using the crane that is moving like this, okay, you get the value, which is again 100, which is different than if you're moving like this. Because if you're moving another direction, the total strain energy will be different. And that's where you need to be very careful. Because if you kick out these members that are not contributing much to this motion or this deformation, they may be very critical to other direction. So that's why you need to be, this selection is valid only in the case that you started in advance. Then if you decided to change your motion, you should change the set of the modes you're selecting. Again, using this automated procedure. I don't know what to say about that, but it's one of the best questions in so far in my career. Fantastic question. Thank you. Because I forget to mention that. I'm sorry about that. I thought that I need to explain it, but I forget it. Any other comments? So Team Malaysia, when you gonna go back? You gonna fly back home on Thursday or when? Sunday. All right, Sunday. Okay, so you still have plenty of time to enjoy the good weather. Okay, as promised, it's gonna be 2:05, 2:03 I see. So we're gonna continue next week, and then it's gonna be at noon. So we get started at 12:15. 12:15. Very important. Be here 12:15. Honestly, I don't know what the heck happened. Maybe, okay, but this is not my worst mistake because once I invited a big group of students to come over from another university, and I completely forget that. And I got the phone call like, where you are at, the team is here. And I wasn't even in a university. I was saying, oh, it's going to take a couple more minutes. I'm walking from my office. So it can happen. It can happen. My apology. Okay, guys. See you on Tuesday at noon, 12:30, 12:15, 12:15, of course. Okay, let me close this one.